So this is the very last lecture, the second part of elliptic wings, and this lecture is about the drag. So if you remember from our previous lecture, I told you that when we talk about elliptic wing, we are talking about elliptic elliptic lift distribution, and therefore that produces a elliptic planform. Um, and then we also saw from the previous lecture these quantities, right? We derived those quantities, and I showed you what these quantities are, and actually went further and I expanded on what these quantities look like, right? This is an alpha missing there. So what these quantities look like for many other different cases. So where this is given by for supersonic, etc., etc. Okay, so those expressions can be used to backtrack any of the values that you're looking for. Now, when I talk about drag, there are a couple things to keep in mind. So first of all, we have something called a parasite drag, and that drag includes the form drag, that's basically shape of the aircraft, the skin friction, the interferences such as vortices, etc., etc. And this drag is the lift induced. This drag exists because we have lift. Just the fact that we have lift, we will have a drag. So as you can see, typically we want to do is we want to find where's that optimum location in which we can design our structure. There's not such a thing like a zero drag. As you can see, you're going to have drag minimum. Okay, and this is the velocity. So then here, this plot right here, this plot is the summation, adding this point, all these points together, you will get this parabolic equation. And this is the location that typically this is not the minimum, sorry. So this is the location that we are really looking for, this drag right here. That's the design point. You cannot go any further down than that. Okay. So if we had that, couple more things. The induced drag again is given by this equation, where this is the downwash velocity. Okay, so we are working with this guy right here to find the induced drag. So to do that, we need to find what the downwash velocity is, and I just mentioned to you that's not something that we can avoid. Okay, so to find the downwash velocity, what we have is, we know that this is equal to this, and we can basically replace all the values here, and you can show, I'm not going to go through the whole derivation, but basically this whole thing, if I take the derivative, of this, if you remember, 1 minus 2yb squared, this is, and you take the derivative, this is what you're going to end up with. Then the square root of 1 minus 2yb squared. You can further express this as 4 times gamma sub 0 y b squared square root of 1 minus 2yb squared. We can express that, and then we can actually go and plug everything into a downwash velocity equation that gives you 1 over 4 over pi minus b over 2, and then what you can see is we can use some integration tricks here, so we can actually solve this equation, and this whole integration basically becomes to 1 minus pi gamma sub 0 b squared minus b over 2 b over 2. This gives square root of 1 minus 2 times eta b squared, eta y minus eta d eta. We can do a couple of substitutions here. B over 2, cosine of theta. We can use eta equal to b, same expression, cosine of eta. And then d eta would be minus b over 2 sine of theta. And then we can replace everything, plug everything inside. I'm sorry, this is phi. This is phi. So we can plug everything inside there, and we can show that, knowing that this integral is equal to this, and the end equation is what I really care for. This is the downwash expression for downwash velocity for an elliptic distribution. Okay, to better understand this, so the whole expression here, if I plug in all the expression, you find that this is your gamma is equal to that, and you find that gamma is equal to this as well, and then from here and combining this term and this term, you can show that downwash velocity can give you this if you knew the total amount of lift as well in a problem. So these expressions are great because what they actually tell me is, if I know my downwash velocity, then I can know what my drag is. Okay, and to know what your drag is, then you induce drag going back inside here, plugging everything in there and showing that this is equal to this. You can show that your total drag in your problem is actually equal to this nice equation right here. Okay. So in other words, for elliptic wings, you can show that di is equal to gamma sub 0 L 2 pi v infinite. That's your induced drag. Your drag in the problem, this is given by b over 4. The total drag expression will be pi over 8 gamma sub 0 pi. So this is just the induced drag. This is the drag in my problem. And then if I continue, you can further work in some expressions here. If you remember, we showed that this was equal to c sub 0 over 4. And so I can also show you that this was equal to b over s, gamma sub 0 v infinite. Then your CDI will equal to your DI 1/2 rho v squared s. And this total thing is equal to 4 times s, gamma sub 0 v infinite squared. And you can replace all this value in there and show that the whole thing gives you pi AR. So basically, if I know my coefficient of lift, since this is actually a consequence, remember this exists because this guy exists. So therefore, if I just know this, I can immediately find what my induced drag is using my lift, pi and your aspect ratio. Okay. Other variations of these expressions are 1 over pi, s over b squared, cl squared. Also another small variation of that. Okay. So from here, you have CDI is equal to cl squared, pi AR squared. And know something very interesting, right? If we just plot this, this is equal to pi AR CDI, or just, and we plot this respect to this, and you can see what happens. then what happens is as this actually goes to infinite, aspect ratio goes to infinite, your induced drag tends to 0. The other aspect of this is the following. The couple things when we talk about induced drag, there are a couple of data, right? So your lift data, your induced drag data is given in 4 digits, and the way we talk about this in counts. So if I say 100 counts, it means 0.0100. If I say 1 count is 0.001. If I say 1,000 counts, then it will be 0.100. This will be 1,000 counts. Okay, that's how this is really measured. Your coefficient of lift typically is given in 2 decimal points, and you have another value there. The most general expression that you can have is given in this plot right here, where your K is actually this expression right here, this whole thing. This is the Oswald efficiency factor. Then what we can also do is the total drag is actually going to have a couple of components, right? And to know what this component is going to come from this plot, from a plot of CD over CL. It's going to be the minimum value that it has. That minimum value is right here. That is this value here. And that is this value that will go here, or this, right? That's the minimum drag. It's 0.017 for this particular case. And then here, one way to approximate your E will be 1 plus 2 times H is the thickness. So this is the airfoil thickness. This is the thickness of your airfoil divided by 2 times that divided by the span. Your total wingspan, right? The total wingspan of the airfoil. These are the final expressions that we use. This comes from tables. In order to find what this table is, you can use this, where this is the average chord. Then you can use this table right here. This is flat plate. This is a very good assumption for thin airfoils. However, sometimes we can get the value and multiply by a correction factor. We can also use these values here. You can be as accurate as you want, but sometimes we can just accept values that we got from these tables here from many different cases. Okay, so in the last section, we're just going to do one example and see how all this theory works together.